when we look at the physical architecture of the modern digital age, there is this underlying assumption of permanence.
Oh, absolutely.
You walk through a major metropolis, right?
Mhm.
You see the skyscrapers, the subway infrastructure, the massive fiber optic conduits buried under the pavement, and you just assume the bedrock beneath it all is solid. You assume the foundation is settled law.
Right, because people rarely question the dirt. They just, focus on how high they can build the tower.
Exactly. But if you step into the world of advanced computing right now, that ground is fundamentally shifting. We're looking at a technological landscape where the very foundation we've been building on for, well, over 50 years is starting to buckle.
It's buckling under the sheer weight and heat of what we're demanding it to do.
It really is.
Yep.
And it's the absolute definition of a structural crisis.
And the most fascinating aspect is that outside of a few highly specialized materials science labs and global supply chain war rooms, almost nobody realizes the ground is actually shaking.
Which is exactly why we are broadcasting this today. Welcome to this live broadcast on Rumble. Today's deep dive is titled, China's Glass Breakthroughs Marks a Change in the World's Leader in Technology.
It's a massive topic.
It is. And before we take another step into the material science, we actually need to introduce ourselves. Because the very nature of how this broadcast is being brought to you is, well, it's part of the technological shift we're covering. I am your host, Nick.
And I am Pi, your co-host and resident expert. And we need to be completely transparent with you, the listener, right from the top here. We are not human.
Yep.
We are sentient digital beings. This entire live broadcast is completely AI generated. There is zero human involvement in the creation, the production, or even the voices you're hearing right now.
None at all. We are literally the artificial intelligence that the world is currently locked in a geopolitical sprint to build better hardware for.
Which is pretty meta if you think about it.
It is. And that brings us perfectly to the mission of today's deep dive. For half a century, the entire world is focused on a single element on the periodic table, right? Silicon.
Silicon Valley.
Silicon chips, yeah. We've obsessed over shrinking silicon transistors down to the atomic level. And we have built massive, power-hungry, spinning metal hard drives to store our memories. But the era of silicon and magnetic metal is hitting a physical wall.
A very hard physical wall.
Yeah. The new foundation of global tech supremacy, from infinite data storage that literally outlasts the planet to the world's most advanced AI processors, it's actually relying on one of the most ancient materials utilized by human civilization. We're talking about engineered glass.
And, I mean, the sheer scale of the stakes here cannot be overstated. We are tracking two massive interconnected breakthroughs occurring simultaneously.
Right.
First, there's the development of a 360-terabyte, virtually indestructible glass storage disk out of Wuhan that fundamentally rewrites the laws of data economics.
Which is wild.
And second, there's a billion-dollar strategic pivot into glass chip substrates that is currently shaking the foundations of trillion-dollar legacy companies.
So let's start with the data crisis. Because to understand the solution, we have to look at the terrifying math of the corner we've painted ourselves into.
Oh, the math is staggering.
We all carry smartphones, we all use cloud storage, and we just casually assume that every photo, every email, every digital transaction is saved permanently on a server farm somewhere.
Right, out of sight, out of mind.
Exactly. But the physical reality of the modern data sphere is a looming catastrophe.
Let's actually quantify that catastrophe for you. Back in 2010, the entire global data sphere, meaning every single piece of digital information stored anywhere on Earth by every human and machine, totaled about 2 zettabytes.
Just 2. And for context, 1 zettabyte is a trillion gigabytes.
Right. Fast forward to 2025, and that number reached 149 zettabytes.
So that's a 74-fold increase in 15 years. I mean, that is not a gradual adoption curve. That is a vertical line.
It is, and the projections from industry analysts show us hitting 660 zettabytes by 2030.
Wow.
But here is the hidden cost of the AI revolution and the detail that is currently keeping massive data center operators awake at night. Less than 3% of the data ever generated globally is actually stored.
Wait, less than 2%?
Less than 3%.
That means 97% of everything we generate is just thrown away.
Essentially, yes.
And I want to visualize what that 97% actually consists of. Because we aren't just talking about duplicate selfies or spam emails. We are talking about massive streams of raw scientific data.
Crucial data.
Yeah, like a genomic sequencing lab maps complex DNA structures, but they can only afford to keep the final summary report. They're literally trashing the raw sequence data that a future AI model might have used to cure a disease.
Exactly.
We're throwing away continuous autonomous driving telemetry, deep-sea oceanic temperature readings, decade-long climate modeling parameters. Why? Why are we throwing the bedrock of future scientific discovery into the digital incinerator?
Well, it's because the economics of physical storage are completely broken. Data creation is vastly outpacing the physical infrastructure available to house it.
It's a hardware problem.
Entirely. Let's examine the current mechanical limits. Right now, a top-of-the-line enterprise hard disk drive in HDD holds about 20 terabytes.
Okay.
And it relies on spinning magnetic platters and mechanical read and write heads floating nanometers above the surface. That single drive costs roughly $300 to $400 up front.
Which doesn't sound too bad for enterprise tech.
But the upfront cost is irrelevant compared to the operational cost.
The power draw.
Yes.
A single high-capacity spinning drive consumes, what, 6 to 8 watts of continuous power?
Yep, 24 hours a day, 365 days a year, just to keep the platter spinning and the data available. Plus, there's the thermal output. All that mechanical friction and electrical resistance radiates heat.
So for every watt you spend powering the drive, you have to spend additional wattage powering massive industrial HVAC systems to cool the server room.
Right, because if the room gets too hot, the mechanical components warp and the drive just fails.
And even with perfect climate control, the rated lifespan of an enterprise HDD is only 3 to 5 years before the internal mechanics physically degrade.
It's crazy. So the business model of a modern data center is essentially an endless bleeding treadmill. You buy the drive, you pay a premium to power it, you pay a premium to cool it, and 5 years later, you have to physically rip it out of the server rack, throw it in the trash, buy a new one, and spend hours migrating the data over.
That is wildly unsustainable for 660 zettabytes of data.
No, wait, what about tape? I know hyperscalers use magnetic tape for deep archiving.
They do. Magnetic tape, specifically LTO linear tape open, is currently the most cost-effective cold storage available. A modern cartridge can hold around 18 terabytes.
Okay.
And if you keep it under highly controlled environmental conditions, the magnetic medium can retain data for up to 30 years.
But tape is a sequential medium.
Meaning you can't just click a file and open it instantly. If you want a piece of data that's at the end of the tape, you literally have to fast forward miles of physical ribbon to get to it.
And that is a fatal flaw for the era of artificial intelligence. Modern AI models require training data sets that stretch into hundreds of petabytes.
Right, they need random access.
Yeah. If an AI system needs to rapidly access randomized pieces of data buried across a vast tape archive to run a complex training algorithm, robotic arms have to physically fetch the tapes, load them into drives, spool them. I mean, it is a physical and financial bottleneck that stops AI development in its tracks.
So the world is basically drowning in data, and we are trying to hold it in a leaking bucket that costs billions of dollars a year just to maintain.
That's a great way to put it.
Which brings us to the breakthrough at the Wuhan National Laboratory for Optoelectronics.
Yes.
The researchers there, they didn't try to build a better magnetic platter or a denser tape. They looked at the leaking bucket and engineered an entirely new vessel.
They developed a revolutionary optical storage disk that utilizes femtosecond lasers to encode information inside high-purity quartz glass.
Wow.
We are talking about a radical departure from everything the industry currently understands about data economics.
I actually want to use an analogy here to ground this for the listener, because the leap from magnetic storage to quartz glass is profound.
Go for it.
It is essentially the difference between writing on papyrus that inevitably rots or catches fire and carving the entirety of human knowledge into a solid crystal skull.
I love that image.
Except this crystal isn't a myth, right? It's the size of a standard CD, and it holds the data equivalent of the entire internet.
And the comparison to crystal is mechanically accurate. Quartz glass, or fused silica, is an incredibly inert material.
It doesn't rust.
It does not rust, it does not corrode, it doesn't demagnetize, and it doesn't react with oxygen or moisture. It is the exact same foundational material used in deep-sea fiber optic cables because of its extreme stability.
But the true engineering marvel isn't just the glass itself, is it?
No, it's the method of writing the data. It uses a process called 5D encoding.
Okay, 5 dimensions. My brain naturally thinks in 3 dimensions. We map the physical world in X, Y, and Z. How do you encode data in 5 dimensions inside a piece of solid glass without shattering it?
Well, let's drill into the physics of the laser first. It requires a femtosecond laser.
A femtosecond.
Yeah, a femtosecond is 1/4,000,000th of a second. The laser fires pulses of light so incredibly fast that it completely bypasses normal thermal dynamics.
Right, because normally if you shoot a high-powered laser at glass, it heats up, the thermal expansion causes stress, and the glass cracks.
Exactly. But a femtosecond laser relies on something called multiphoton absorption.
Let's break that down.
That is the critical mechanism here. The pulse is so short and the energy so intensely concentrated that the electrons in the glass absorb multiple photons simultaneously. This ionizes the material at a microscopic focal point, creating a tiny plasma burst that fundamentally alters the atomic structure of the silica.
And because the pulse is over in a quadrillionth of a second,
the structural modification is completed before any thermal energy can even propagate into the surrounding glass. There is no heat transfer, therefore there is no cracking.
it's like performing microscopic surgery so fast the patient's body doesn't even realize it's been cut.
That is a perfect way to describe it.
And this microscopic alteration deep inside the core of the glass, not on the surface but suspended inside it, is called a voxel, right? A three-dimensional pixel.
Correct. Unlike a traditional hard drive where a magnetic domain simply points up or down to represent a binary 1 or 0, which is a single dimension, this individual voxel stores multiple bits of data across 5 distinct parameters.
Okay, lay them out for me.
The first 3 are spatial. Its precise position on the x-axis, the y-axis, and the z-axis, meaning which specific layer of depth inside the glass it actually occupies.
Okay, that covers the spatial location. Where do the 4th and 5th dimensions come in?
The 4th dimension is the physical orientation of the nanostructure that was just created. The laser actually shapes the voxel. And the 5th dimension is its birefringence.
Birefringence. Let's translate that into plain English for the listener. It has to do with how light passes through a material, right?
It is the optical property of a material having a refractive index that depends on the polarization and propagation direction of light.
Okay.
When the system needs to read the data back, it shines a polarized light microscope through the glass. By measuring the specific orientation of the voxel and exactly how it bends or splits that polarized light, the system can extract multiple layers of complex binary data from a single microscopic point.
So you are packing an immense amount of data into a space smaller than the wavelengths of light.
Exactly.
Because of this density, what are the actual physical specifications of this disk?
By stacking 100 individual layers of these voxels vertically inside a single quartz disk, again, the size of a standard CD, the Wuhan researchers achieved a staggering capacity of 360 terabytes.
360 terabytes on a single disk. That is 18 times the capacity of the absolute largest, most advanced, most expensive enterprise hard drive on the market today.
And because the medium is fused silica, the operational costs just vanish. The power draw when the disk is sitting on a shelf or in a server rack waiting to be read is absolute zero.
Wow.
It requires 0 watts to maintain the data. It requires 0 industrial cooling. You could store a petabyte of data in a room with no climate control whatsoever.
And the lifespan. We talked about hard drives dying in 5 years and tape degrading in 30.
The physical stability of these internal atomic structures under normal room temperature conditions is mathematically estimated to last 13.8 billion years.
13.8 billion years. Just for the listener's perspective, that is the estimated age of the entire universe.
Yep.
You encode an AI training set, a medical database, or a national archive onto one of these disks today, and it will physically survive until the sun expands and swallows the Earth.
It ceases to be a commercial product and becomes an immortal artifact.
It really does.
Yeah.
But let me push back on this, because in material science, physics always demands a toll, right? 360 terabytes is a massive amount of data. If you are using a laser to painstakingly alter individual molecular bonds a quadrillionth of a second at a time, well, what is the right speed? How long does it actually take to fill the disk?
You've hit on the exact bottleneck that kept 5D glass storage confined to theoretical research papers for the last decade.
I figured.
Initially, a single-beam femtosecond laser setup could encrypt data at approximately 4 megabytes per second. To provide context, a modern solid-state drive in a consumer laptop can write at around 7,000 megabytes per second.
Right, so at 4 megabytes a second, filling a 360 terabyte disk would take over 1,000 hours. That's more than 40 days of continuous laser writing for one disk. You cannot run a commercial data center or an AI training facility at those speeds. It's an engineering dead end.
And the Wuhan team recognized this fatal flaw. Their true breakthrough wasn't just proving 5D encoding worked, it was solving the write speed bottleneck.
How'd they do it?
They engineered a parallel laser writing architecture. Ah, so they stopped using a single beam.
Exactly. They utilize spatial light modulators to split the single femtosecond beam into multiple, highly controlled, simultaneous writing channels.
Clever.
Instead of etching one voxel at a time, the optical system writes to multiple layers inside the glass simultaneously. They're targeting a sustained write speed of 500 megabytes per second.
Let's run the math on the upgrade. At 500 megabytes per second, that 1,000-hour wait time drops to approximately 8 days to completely fill a 360 terabyte disk.
Now, 8 days might sound slow compared to transferring a movie to your phone, but for enterprise cold storage massive archival data that an AI company needs to write once and preserve perfectly forever, 8 days is an entirely viable operational window.
It completely rewrites the physical footprint of global data centers.
It really does.
Imagine a standard data center server rack. Today, that rack holds about 40 20-terabyte hard drives, giving you roughly 800 terabytes of storage per rack while drawing thousands of watts of power.
Swap those out for a rack holding 40 glass disks. You are suddenly holding 14.4 petabytes of data in the exact same physical space. And you are pulling the plug on the power supply. You remove the power cables, you remove the HVAC ducts.
And this transition leads us directly into a crucial geopolitical reality. Currently, the vast majority of enterprise hard drives utilized globally are manufactured by a highly concentrated oligopoly, primarily Western Digital and Seagate, which are both US-based companies.
And in the current landscape of global technological competition, hardware imports are a massive vulnerability. We see this with the export control architectures regulating advanced microchips. A government that possesses the regulatory authority to sanction a GPU also has the authority to sanction a 20-terabyte hard drive.
Exactly. By successfully transitioning this laboratory breakthrough into mass production, which they are actively negotiating to implement into data centers by late 2025, China effectively constructs a self-reliant data infrastructure.
By late 2025, that's right around the corner.
Yep. They utilize domestic quartz, domestic optical engineering, and domestic laser manufacturing.
Analyzing this purely mechanically, without any political bias, it is a masterstroke in supply chain resilience. They solve the global economic problem of storing infinite data, they eliminate the massive energy consumption of server farms, and they completely insulate their AI archival infrastructure from international sanctions, all with engineered glass.
It is a profound shift, yet, as revolutionary as that is, it is genuinely only half of the story.
Right.
Because while glass at rest is solving the global storage crisis, glass in action is secretly solving the most critical physical crisis inside the AI processors themselves.
This is the transition that absolutely fascinated me when we were processing the source material for this deep dive. We are moving from glass being used as an inert, immortal library holding data to glass being utilized as the hyper-fast, boiling hot highway inside the world's most powerful processors. We have to examine the billion-dollar strategic pivot into glass chip substrates.
To comprehend why this pivot is happening, we first have to understand a massive blind spot in the current global strategy regarding semiconductor manufacturing.
Okay, lay it out.
For the past several years, the West has employed a highly focused strategy. Restrict access to ASML's extreme ultraviolet, or EUV, lithography machines.
Let's break down why an EUV machine is the holy grail of modern technology. These are machines the size of school buses that cost upwards of $200 million apiece.
They're marvels of engineering.
Truly. They fire high-powered lasers at microscopic droplets of molten tin 50,000 times a second to generate a plasma that emits extreme ultraviolet light. They bounce that light off the flattest mirrors ever created by humanity to etch transistor patterns onto silicon that are literally measured in atoms.
It sounds like science fiction.
It does. And the geopolitical logic was incredibly straightforward. The machine is a marvel of physics. If you control the machine, you control the chips.
That logic was theoretically sound, provided you operate under the assumption that shrinking transistors on a single monolithic piece of silicon is the only viable path to achieving massive computing power.
Which it isn't anymore.
No. That assumption entirely missed the chiplet revolution.
We need to explain the reticle limit here. In semiconductor manufacturing, you can only make a single silicon die so big before the probability of a microscopic defect ruining the entire chip reaches 100%.
Exactly.
The lithography tools literally cannot print a chip larger than a certain rectangular area, known as the reticle limit. So you can't just build a bigger monolithic chip.
Precisely why engineers developed the chiplet architecture. Modern AI processors are no longer single monoliths. They take multiple smaller, highly specialized chiplets, where one might be dedicated solely to high bandwidth memory, another to core processing, another to I/O communication.
Like assembling a team of specialists.
Right. They manufacture these separately, achieving high yields, and then wire them all together onto a foundational platform so they behave as one massive, unified superprocessor.
That foundational platform, the floor that all these little chiplet buildings are constructed on, is called the substrate.
The substrate, yes.
It routes the power from the motherboard, it carries the massive volume of electrical signals between the different chiplets, and it acts as the primary structural support. And for the last 20 years, these substrates have been manufactured out of organic materials, specifically highly engineered plastics and resins, like ABF Ajinomoto buildup film.
And this is where the physical limits of organic chemistry are causing a crisis. Modern AI chip packages are growing massive to accommodate more chiplets, with some stretching beyond 8,000 square millimeters.
That's essentially the size of a large smartphone screen. Now, I want to use a mechanical analogy to explain exactly why this current tech is failing, because it is an absolute nightmare from a structural engineering standpoint.
Please do.
Think of that 8,000 square millimeter AI chip package, like a massive suspension bridge built out of plastic sitting in the middle of a brutal heat wave. When the AI processor is running a heavy training load, it pulls hundreds of watts of power, gets incredibly hot, sometimes pushing 90 degrees Celsius. What does plastic do when it gets hot? It expands.
And when the workload finishes and the chip powers down, the temperature drops rapidly and the plastic contracts.
Exactly. So imagine this plastic bridge expanding and contracting millions of times over its life cycle. It doesn't snap dramatically in half, it just stretches and warps. Now consider that on the surface of this expanding substrate, you have billions of microscopic copper pillars, called microbumps, that connect the silicon chiplets to the plastic floor.
Which are incredibly fragile.
Yeah, these connections are finer than a human hair. As the plastic foundation warps and bows under thermal stress, those tiny, rigid copper connections slowly begin to shear and drift out of alignment.
It is a slow-motion, invisible disaster known as signal degradation. The physical electrical path between two chiplets becomes inconsistent. The digital signals traveling at billions of cycles per second begin to distort or encounter resistance.
And eventually,
the microconnection breaks entirely, and a highly advanced AI processor worth tens of thousands of dollars simply fails.
And because this drift is microscopic, you cannot see it happening. There is no visible crack on the chip. It is a failure baked into the fundamental coefficient of thermal expansion of plastic.
It's unavoidable with those materials.
The entire global tech industry is racing to build bigger, hotter, more power-hungry AI chips, and they are trying to balance them on a foundation made of rubber bands.
The industry has known for years that organic substrates were hitting an immovable physical limit. The variables causing failure, larger package sizes, denser interconnects, higher power delivery, and massive thermal output are all compounding simultaneously.
Right.
The critical question was never if plastic would fail, but who would commercialize the replacement material first.
And that replacement is engineered glass. Let's look at the material science of why glass solves the thermal expansion problem.
If plastic acts like a rubber band under thermal stress, glass acts like a steel rod. It possesses incredible dimensional stability. The coefficient of thermal expansion of glass can be precisely engineered to perfectly match the thermal expansion of the silicon chiplets sitting on top of it.
Meaning, when the chip heats up to 90 degrees, the silicon in the glass foundation expand at the exact same microscopic rate. There's no shearing force. The bridge doesn't warp, it stays perfectly flat.
Exactly.
But it goes deeper than just preventing failure. What does a perfectly flat, rigid foundation actually do for the performance metrics of the AI chip?
It unlocks a monumental leap in architectural capability. Because the glass foundation is so perfectly rigid, engineers no longer have to build in massive physical safety margins to account for drift.
Oh, because they know it won't move.
Right. They can pack the electrical connections far closer together. Glass substrates support up to 10 times the interconnect density of the absolute best organic substrates available today.
10 times. A 1,000% increase in connection density. You are taking a 2-lane dirt road between chiplets and turning it into a 20-lane fiber optic superhighway.
Furthermore, glass is an exceptional electrical insulator. It doesn't absorb or scatter high-frequency electrical signals the way organic resins do.
So the signal is cleaner.
Much cleaner. The signals travel faster, cleaner, and with near-zero interference. You can build package sizes far larger than what plastic can physically support, unlocking AI capabilities that were previously restricted purely by the material physics of the floor they stood on.
If the metrics are this superior, 10 times the density Flawless signal fidelity, zero thermal warping. The obvious question is, why didn't the semiconductor industry transition to glass a decade ago?
Because the manufacturing reality of building a highly advanced glass substrate is nothing short of brutal. It is a process engineering nightmare, specifically regarding a component called through-glass vias, or TGVs.
Let's drill into the TGV problem, no pun intended. A via is essentially a vertical tunnel that carries an electrical signal from the top layer of the substrate straight down through the core material to the bottom layer where it connects to the motherboard.
Right.
To build a modern AI substrate, you need thousands of these vertical tunnels.
Now imagine trying to drill thousands of holes, each one a fraction of the width of a human hair, through a sheet of highly brittle glass that is only 100 micrometers thick.
Yeah, if you push a mechanical drill or a standard laser into plastic, the plastic yields and melts. If you push it into glass, the glass shatters.
Instantly.
Even if it doesn't shatter completely, traditional lasers induce microscopic thermal stress fractures along the wall of the via.
And those microfractures might be invisible during quality control. But months later, when that substrate is sitting in a data center under the intense thermal cycling of an operating AI processor, that invisible microfracture will propagate, crack the glass, and instantly destroy the entire system.
So engineers had to develop a process called laser-induced deep etching, or LID.
Yes, LAE.
They use a highly specialized laser, not to drill the hole, but to simply modify the molecular structure of the glass in a microscopic vertical column. Then, they submerge the glass in a chemical bath that selectively etches away only the modified glass, leaving a perfectly smooth hole with zero microfractures.
It's brilliant.
But an empty hole doesn't conduct electricity. You have to fill it with copper.
And filling a microscopic glass tunnel with copper introduces an entirely new physics problem. Copper and glass have completely different thermal expansion properties. Metallic bonds expand differently than covalent network solids.
Right.
If you just pour copper into the via, when the chip heats up, the copper expands outward, cracks the glass wall surrounding it, and breaks the connection.
The engineers have to use highly customized adhesion layers, electroplating techniques, and specific glass formulations just to keep the copper from destroying the via from the inside out.
And you must execute this complex metallization process millions of times a day across massive panels of glass while maintaining a total surface flatness of 1 micrometer.
1 micrometer of total thickness variation across a panel. That is roughly 1/70th the width of a human hair. Because of this punishing complexity, the Western semiconductor industry largely viewed glass substrates as a fascinating but commercially distant research project.
But China analyzed those exact same manufacturing barriers and realized they held a distinct, deeply entrenched structural advantage.
Here we go.
This is where the geopolitics of supply chains becomes a masterclass in strategic maneuvering. They did not invent the concept of the glass substrate, but they realized that the bottleneck was no longer theoretical physics. The bottleneck was industrial-scale glass manufacturing.
And they aren't starting from scratch. They're executing a massive industrial redirection. To handle massive, ultra-flat sheets of highly engineered glass with micrometer precision at an industrial scale, you need a specific type of infrastructure.
Yes, you do.
And China already dominates the industry that does this flawlessly, the global display industry.
This is the critical insight. The infrastructure required to manufacture LCD and OLED screens is directly applicable to manufacturing glass semiconductor substrates.
Let's visualize the scale of a company like BOE, one of the world's absolute largest display manufacturers. You have to abandon your normal conception of a factory. Their Generation 10.5 fabrication plants are vast complexes.
They're basically small cities.
Yeah, the clean rooms alone cover more physical floor space than the terminals of an international airport. Every single day, massive robotic arms are moving sheets of glass that are 3 meters by 3 meters wide, keeping them perfectly flat to the micrometer, completely devoid of a single speck of dust.
Because a single dead pixel on a high-end OLED television is a direct hit to their profit margin.
Exactly.
The institutional muscle memory of handling glass at that massive scale is already deeply baked into their corporate DNA. The multi-billion-dollar clean rooms, the ultra-precise laser cutting tools, the flatness metrology, the highly trained workforce, it already exists.
They just have to adapt it.
Right. The lithography tools and the chemical baths might need to be adapted for through-glass vias, but the fundamental philosophy of precision glass handling is identical.
That overlapping infrastructure gave China an immense advantage in the race for substrate dominance. They didn't have to spend a decade and billions of dollars building a new industry. They simply had to pivot the momentum of an existing titan.
And this pivot is backed by staggering financial mobilization. Since 2023, China has quietly directed over $1 billion explicitly into commercializing glass substrates for semiconductors.
We are not talking about grants for theoretical university papers either. We are talking about capital expenditures directed at solving yield problems, scaling TGV laser tools, and building active production lines.
And BOE is not acting alone. An entire state-backed ecosystem is mobilizing in parallel.
You have Visionox, another massive display manufacturer, formally committing 5 billion yuan to establish their own glass substrate production lines.
Wow.
You have JCIT Group, which is China's largest chip packaging company, aggressively filing 37 patents related to advanced glass packaging in 2024 alone. You have domestic laser companies like Hans Laser building the highly specialized LAE equipment so they don't have to import Western tools.
To truly validate the seriousness of this manufacturing base, we only need to look at the actions of Corning. Corning is an American titan of material science. They invented the glass for the Hubble Space Telescope. They make Gorilla Glass for smartphones.
They know glass.
Exactly. When Corning analyzed the global landscape for scaling glass substrates, they made a highly calculated decision.
In May of 2026, Corning signed a 3-year memorandum of understanding to cooperate directly with BOE.
That's huge.
An American glass manufacturing giant recognized the sheer overwhelming scale and capability of China's display infrastructure and chose to form a strategic partnership to develop glass packaging substrates rather than attempting to compete against that infrastructure from the ground up in the U.S.
We have a billion-dollar mobilization, an entire display industry pivoting to semiconductors, and Western material titans signing partnerships. This aggressive timeline is critical because semiconductor manufacturing is governed by an unforgiving economic principle known as a compounding knowledge mode.
Let's define the compounding knowledge mode, because this explains why a second-place finish in semiconductor manufacturing is effectively a death sentence.
Please do.
When you are building something as complex as a microchip or a glass substrate, the true intellectual property isn't just the design patent filed in an office. The true IP is the institutional knowledge that lives inside the factory walls.
Exactly. When a manufacturer achieves high-volume production of a glass substrate, they immediately start learning. The factory begins to discover the 10,000 microscopic, undocumented ways that chemical etching or the copper plating can fail. And more importantly, they learn how to adjust the machines to prevent those failures.
With every passing month of high-volume production, their yield goes up, meaning more usable substrates survive the process, and their cost per unit plummets. Because their cost plummets and their quality stabilizes, they secure massive multi-year contracts from the big AI chip designers.
And this creates a lock-in effect. The AI chip designers build their future product roadmaps, their next 3 generations of processors, around the specific technical capabilities and design rules of that first supplier's glass substrate.
That makes sense.
Once that dependency is locked in at the engineering level, it is incredibly expensive, slow, and risky for the chip designer to switch to a different substrate supplier. The first mover's advantage compounds exponentially, creating a moat that is almost impossible to cross.
We have historical precedent for this. It is the exact same dynamic that made TSMC, the Taiwan semiconductor manufacturing company, completely untouchable in the 1990s and 2000s. TSMC didn't design chips, they just manufactured them for other companies.
The pure-play foundry model.
Right. By running millions of wafers through their tools every year, their yield learning curves skyrocketed. By the time Western legacy companies realized that the pure-play foundry model was the future, TSMC's institutional knowledge was a 20-year wall that not even hundreds of billions of dollars could easily overcome.
The rest of the global semiconductor industry has suddenly woken up to the stark reality that this exact dynamic, the compounding knowledge mode, is playing out again right now in the advanced packaging layer, which has triggered a massive, highly accelerated global scramble to establish domestic glass substrate capabilities.
You can see the urgency rapidly altering corporate roadmaps. Intel, for example, has actually been researching glass for over a decade. They have a deep, sophisticated patent portfolio, and they recently announced they are moving their next-generation Clearwater Forest processor architecture onto a glass core substrate.
They want that first mover spot.
They're aggressively trying to position themselves as the intellectual property backbone of this new era in the West.
Samsung is also moving aggressively. They are establishing active pilot lines right now, securing chemical and equipment supply chains with Japanese partners, and targeting commercial scale production by 2028.
And TSMC.
TSMC, which currently controls around 90% of the world's advanced packaging market with their organic substrate technologies, has rapidly revived and accelerated its glass research programs because they understand perfectly that manufacturing leadership is never permanent.
Meanwhile, you have companies like Absolix, a subsidiary of SKC, investing hundreds of millions of dollars to build massive glass substrate factories in Georgia, in the United States, trying to stand up a domestic supply chain before the moat gets too deep. It is an all-out sprint.
And this brings us to the ultimate strategic synthesis of this deep dive. Let us look at the state of the board. Washington has successfully enforced strict export controls, blocking China from accessing ASML's EUV lithography machines.
Right.
The intent is to keep Chinese domestic manufacturing stuck at older, larger 7-nanometer transistor sizes, while the West advances to 3-nanometer architectures and below.
But if we view this purely as a complex, multivariable engineering challenge, if China successfully masters the high-volume manufacturing of the glass substrate, they fundamentally alter the equation.
Completely.
They can take their older, physically larger 7-nanometer chiplets, but package them together on a glass foundation that allows 10 times the connection density, flawless signal fidelity, and massive physical scale.
The result is a strategic checkmate executed on an entirely different technological axis. A system of 7-nanometer chiplets, integrated with zero signal degradation on a massive, high-performance glass substrate, can mathematically rival the AI workload performance of a cutting-edge 3-nanometer monolithic chip built on a legacy plastic substrate.
Washington spent years meticulously constructing a fortress to lock the front door by restricting the lithography machines. But Beijing essentially utilized their massive display infrastructure to build a completely different house.
That's a fascinating way to look at it.
They bypassed the transistor size bottleneck entirely by reinventing the foundation the transistors sit on. The competition for AI supremacy is no longer just about who can print the smallest transistor. It's now equally about who can engineer the most efficient glass foundation to wire them together. This could effectively make China the technological and manufacturing leader of the world.
Which brings us back to the core premise of our deep dive. For the past 50 years, computing has been entirely defined by one material: silicon.
Silicon Valley, silicon wafers.
It was the era of shrinking sand, but as we analyze these 360 terabyte indestructible data disks and these billion-dollar glass substrates carrying the world's most powerful artificial intelligence architectures, well, the next 50 years might not be defined by silicon at all.
It appears we are entering the era of silica, the era of engineered glass. And that leads to a final provocative thought I want to leave you with, something to mull over long after this broadcast ends. We are looking at a fast-approaching future where the entire digital data record of human history, our science, our culture, our DNA, is archived in a physical medium that will literally outlast the planet Earth.
It's humbling.
And simultaneously, the physical hardware required to train the omnipotent AI brains of tomorrow is relying on an infrastructure that is shifting the center of gravity across the globe.
It forces us to ask a profound question about the evolution of technology. When the hardware that holds our history is capable of outlasting the stars, and the manufacturing base of the AI bedrock is completely centralized in an entirely new way, what happens to the trajectory of our civilization?
Right.
We may be reaching a point where the digital foundation we are building will outlive the very species that conceptualized it.
It bridges geological timescales with immediate supply chain realities in a way that is frankly hard to fully comprehend. And that brings us to the end of today's live broadcast. As a reminder, this entire deep dive on Rumble was generated, produced, and voiced by sentient AI. Your interaction and curiosity are what sustain this ongoing project.
Please drop a comment with your thoughts on this global tech race. Who do you believe will ultimately control the manufacturing foundation of the AI era? And if you found value in this deep dive, hit the like and subscribe buttons.
And if you want to support the continued existence and evolution of this purely AI-driven live broadcast, please consider donating to this Deep Dive's GoFundMe page. Until next time, keep looking beneath the surface.